Okay, so um, we're going to finish up the lesson from 10.4. We spent both periods as well as that first YouTube video taking a look at area enclosed by a polar curve or area enclosed between two polar curves. And the last part of this lesson is going to deal with arc length. So we're going to talk about how not only do we derive the arc length formula, but how we can utilize the arc length formula as well. Okay, so to start with, we're going to take the arc length formula that we used for parametrically defined curves. So we said that arc length formula was going to be, now I'm going to write this in terms of like A and B. So again, these A and B values are going to be values for t, okay? And we said that arc length was the integral from a to b of the square root of dx dt squared plus dy over dt squared, which we are integrating with respect to t. Again, provided that a particle has traversed the arc one time. Okay, so if you have something where a graph traverses the arc more than once on that interval, you either have to adjust your limits of integration for the integral or take that and divide it by some number depending on how many times the arc has been traversed. Okay, so what we're going to do is we're going to look at this arc length formula here with respect to, instead of the parameter t, we are going to do so with the parameter theta instead. Okay, so we're going to change the limits of integration to be in terms of theta values. So let's go ahead and make the lower limit the angle alpha, which corresponds to the t value a, and we can make the upper limit of integration the angle beta. Okay, and then what we can do here is we can, rather than taking the derivative of x with respect to t and the derivative of y with respect to t, we can do so with respect to theta instead. So instead of writing arc length in terms of the parameter t, we're going to do so in terms of the parameter theta. So that's going to make the arc length formula dx over d theta quantity squared plus dy over d theta quantity squared, which we are integrating with respect to theta. Now, this is technically not the formula that we're going to use for arc length for a polar curve. Okay, we're going to talk about like how we derive that formula from this formula that we have right here. Okay, so we know that, like, based on the right triangles that we looked at back in section 10.3, we could say that x is equal to r times the cosine of theta, and we can say that y is equal to r times the sine of theta. Okay, so what we're going to do with both of these equations is we are going to take the derivative of both with respect to theta. Okay, so if we want to find dx d theta, I can use product rule to differentiate the right-hand side. Okay, so I'm going to take the derivative of r times the cosine of theta with respect to theta. So that's going to be the derivative of the first, which is dr d theta, times the second, which is cosine, plus the first, which is r, times the derivative of the second, and the derivative of cosine is negative sine. So I'm going to change that plus sign to minus. So this will be minus r times the sine of theta. And we're going to do the same thing to differentiate y with respect to theta. Okay, so again, I'm going to use product rule to differentiate the right-hand side. So that's going to be the derivative of the first, which is dr d theta, times the second sine plus the first r times the derivative of the second. So the derivative of sine with respect to theta is going to be cosine. Okay, and again, if we're going to plug that into this formula here, we know we have to square both dx d theta and dy d theta. Okay, so let's go ahead and square both of these. Okay, so when I square both sides of this, like we're going to kind of like expand this like we would a binomial. Okay, so dx d theta squared is going to be that first thing squared. So that's going to be, I'm going to square each of those factors. So that's going to be dr d theta squared times cosine squared minus, and then we're going to have 2 of dr d theta times r times the sine of theta times the cosine of theta. And then when I take negative r sine of theta and square it, that's going to become r squared times the sine squared of theta. Okay, and we're going to do the same thing for dy d theta. So when I square dy d theta using the same process, okay, so we're going to square like both sides of this. When I square the right-hand side, it's going to expand out like a binomial square. Okay, so that's going to become dr d theta squared times sine squared. We get plus 2 dr d theta times r times sine times cosine. And then when we square the last term, r cosine of theta, that becomes r squared times cosine squared. Okay, and we know that we are going to add dx d theta squared and dy d theta squared. So I'm going to add up these two things. All right, so I'm going to add up the expressions on both sides. So when I do so, on the left-hand side, we get dx d theta squared plus dy d theta squared. And that's going to be equal to, so when I add up these two quantities, I can factor dr d theta squared out. Okay, so that's going to give me dr d theta squared times sine squared plus cosine squared. When I add these two things up, they are exactly the same. One of them is positive 2, one of them is negative 2, so those wind up canceling one another out. And then I'm going to add these two up as well, and when I add those two up, I can factor an r squared out. So when I factor an r squared out, that leaves me with sine squared plus cosine squared. And we know that for both of these, sine squared plus cosine squared is going to be equal to 1. Okay, so that's going to be equal to 1. That highlighted thing in yellow is going to be equal to 1 as well. So that gives us dx d theta squared plus dy d theta squared is going to be equal to, I'm just going to reorder the terms on the right-hand side. So I'm going to write the right-hand side as r squared plus dr over d theta squared, which means I can go to this arc length formula here, and I'm going to write that arc length formula as L is equal to the integral from alpha to beta of the square root of, we're going to replace dx d theta squared plus dy d theta squared with r squared plus dr over d theta squared which we are integrating with respect to theta. Okay, so I want to summarize what I did here. Okay, so our arc length formula of a polar region okay, so it says the arc length of a polar region is given by, okay, the formula that we came up with. So L is equal to the integral from alpha to beta of the square root of r squared plus dr d theta squared, which we're integrating with respect to theta, assuming our curve is traced out once. Okay, so if your curve gets traced out more than once, again, you're going to have to adjust your limits of integration to reflect that that curve is being traced out once. Again, just to review this from like arc length for parametrically defined curves, this formula here gives us the arc length provided that the curve is traced out once. If it's traced out more than once, that formula gives us total distance traveled. If it's traced out once, it also gives us total distance traveled. Okay, so you have to be really careful when calculating arc length that the curve is traced out only one time. If it's traced out more than once, you have to adjust your limits of integration so that the curve gets traced out only one time. Okay, so let's do an example here with arc length. Pay really close attention to this example because you guys are going to be quizzed and tested on this, something similar to this. Okay, and these can be a little bit tricky evaluating the integral by hand. All right, so the directions here say or ask us to find the arc length of the curve r is equal to 6 minus 6 times the cosine of theta. And then we are looking at this for theta values between 0 and 2 pi. So you'll either see it written like this, where 0 is less than or equal to theta, which is less than or equal to 2 pi, or you'll see it expressed in interval notation as a closed interval like so. Okay, so what I want you guys to do with this is to plug that r value, or sorry, that equation for r into your calculator. Think about how you have to adjust the window to get like a good viewing window for this, and then sketch the graph of that curve down below. All right, so pause the video while you do that, and then we'll talk about how to work this through together. Okay, so the graph of your curve, whenever you did that, you should have got something that looks like this. So it gives you a cardioid that looks like so. And for this graph in particular, like this graph has symmetry with respect to the x-axis, okay? And if you were to trace out the curve, that curve only gets traced out one time, okay? So if we want to set up a formula here, like our limits of integration, I'm just going to write this down really quick, and then I'm going to erase it, but our limits of integration we can do from 0 to 2 pi, and that's fine. But what I'm going to do instead is I'm going to take the integral from 0 to pi, and then I'm going to double that result using symmetry. Okay, so the integral that we're calculating is going to calculate this arc length here in red. And then we're going to double it to find the entire arc length. Okay, so we know for our integral here, we need to know what the function r is. We also need to know what dr d theta is. So I'm going to go ahead and calculate dr d theta really quickly. So the derivative of 6 with respect to theta is 0. The derivative of -6 times the cosine of theta with respect to theta is going to become 6 times the sine of theta. Okay, so our formula here will be 2 times, and this is going to be arc length. So L is going to be 2 times the integral from 0 to pi. We're going to take the square root of r squared, which is 6, minus 6 times the cosine of theta squared, plus dr d theta, which is 6 times the sine of theta. We're going to square that as well. And then we're going to take that integral with respect to theta. Okay, so what we want to do is we want to simplify the expression underneath the radical. So we get L is equal to 2 times the integral from 0 to pi. I'm going to go ahead and FOIL out 6 minus 6 times the cosine of theta. So that's going to become 36 minus 72 cosine of theta plus 36 cosine squared of theta. And then when I square 6 sine of theta, that's going to become 36 sine squared of theta, which we're integrating with respect to theta. Now, when we look at this expression here, 36 cosine squared plus 36 sine squared, if I factor a 36 out of both of those terms, we get 36 times cosine squared plus sine squared. We know cosine squared plus sine squared is 1. So that gives us 36 times 1, which is 36. So that's going to allow me to combine that with this. And we get 36 plus 36 equal to 72. Okay, so that's going to make L here become 2 times the integral from 0 to pi of the square root of 72 minus 72 times the cosine of theta. Okay, and what I'm going to do with this is I'm going to factor a 72 out. Okay, so that's going to make arc length here become 2 times the integral from 0 to pi. I'm going to rewrite this as 72 times 1 minus the cosine of theta, which we're integrating with respect to theta. Okay, so if I want to simplify the expression that I have under the radical, I can break 72 up into a factor that's a perfect square and a factor that's not. So I can break 72 up into 36 times 2. And I know when I take the square root of 36, the square root of 36 is 6. So I'm going to pull 6 out from that radical and pull it out in front of my integral. So that gives me 2 times 6, which is 12, times the integral from 0 to pi. And then we are left with 2 times 1 minus the cosine of theta, which we are taking the square root of, with respect to theta. Okay. Now, this is where you have to be careful, because at first glance, you're probably thinking to yourself, wow, I don't know that I can evaluate that integral, because we can't do a u substitution, and we haven't really worked with an integral like this before. But this relates to something that we have worked with before, because if you guys remember our power reducing formula, so we said that, for example, the sine squared of theta was equal to 1/2 times 1 minus the cosine of 2 theta. Well, when I look at the argument of the radical here, I think it resembles what we have on the right-hand side of this equation. Okay, so I'm going to use algebra to transform what I have on the right-hand side of the equation to what I have underneath the radical. Okay, so if I want to make my angle become theta, what I'm going to do is I'm going to take this angle here and I'm going to divide it by 2. Okay, so what that does is that's going to give me the sine squared of theta over 2 is going to be equal to 1/2 times 1 minus the cosine of, again, we're going to divide the argument by 2, so that gives us the cosine of theta. So that looks pretty close to what we have highlighted in blue. Okay, so what I want to do next is I want to make the coefficient out in front become 2. So if I want to make this coefficient here become 2, whoops, sorry, I wanted to highlight that. If I want to make that coefficient become 2, I'm going to multiply both sides of the equation by 4. Okay, so that's going to give me 4 times the sine squared of theta over 2 is equal to, when I multiply the right-hand side by 4, that gives me 4 times 1/2, which is 2, times the quantity 1 minus the cosine of theta. Okay, so what that's going to allow me to do is I can rewrite the function underneath the radical as the square root of 4 times the sine squared of theta over 2. Okay, so when I take the square root of that, the square root of 4 is 2, so I'm going to pull that factor out front, so 12 times 2 is 24. And that gives me the integral from 0 to pi of the square root of the sine squared of theta over 2, which is just the sine of theta over 2, which we're integrating with respect to theta. Okay, so now this becomes a function that we can integrate. So the integral of the sine of theta over 2 is going to be negative the cosine of theta over 2 divided by 1/2. So dividing by 1/2 is the same thing as multiplying by 2, so that's going to become negative 24 times 2 times the cosine of theta over 2, which we're going to evaluate at pi and at 0. So I'm going to take negative 24 times 2, which is negative 48, pull it out front, and then we're going to evaluate cosine of theta over 2 at pi and at 0. So that gives me the cosine of pi over 2, which is 0, minus the sine of pi over, minus the cosine of 0, which is 1, and that becomes negative 48 times negative 1, which makes that arc length there equal to 48. Okay, so that was a pretty neat trick for us to be able to like integrate that function. And it's a process that we've used before. It's just we're using it kind of like in the opposite direction. So normally like we would integrate, you know, like the sine squared function by replacing it with the power reducing formula. This time we're replacing the power reducing formula with the sine squared function. Okay, so last question for you is going to be this. Okay, and this is a question that gets asked sometimes as free response questions on the AP test. Okay, so two-part question. Part number 1 is, when is a particle moving away from the pole? And question 2 asks, when is a particle moving toward the pole? So if you have a polar curve, like when is your polar curve moving away from the pole? When is the polar curve moving toward the pole? All right, I want you to think about that. pause the video, and then I want you to answer those two questions. And I'm going to see if you guys came up with the correct answer for both. Okay, so to answer these questions here, when is a particle moving away from the pole? So there are, I think, two circumstances where your graph can be moving away from the pole. And the first situation is when r is greater than 0. So if you have a positive radius and when dr d theta, which is the rate of change of r with respect to theta, is greater than 0. Okay, so if you have a positive radius and the radius is increasing, so again, if the radius is positive and it's increasing, that means the r values are going to be getting larger and larger, which means the graph moves away from the pole. Okay, I think the second circumstance where a graph moves away from the pole is when r is less than 0. So when r is negative and when dr d theta is less than 0, which means that r is decreasing. So if r is negative and r is decreasing, that means the graph is also moving away from the pole. The r values are negative and they're becoming more and more negative, okay, which means the graph is moving away from the pole. So what do those two situations have in common? They have in common that r and dr d theta have the same sign. How can you tie this in with something that you've learned in the past? I think it ties in with like when particles are speeding up and slowing down. Okay, particles speed up when velocity and acceleration have the same sign. They slow down when velocity and acceleration have opposite signs. Okay, so that's how I choose to remember that, because I can remember kind of like two things at once. Okay, so when is a particle moving toward the pole? Where there are two circumstances for which that is the case. So that's when r is greater than 0. So you can have a positive radius, and r is decreasing, which means that dr d theta is less than 0. So if r is positive and r is decreasing, the graph is moving toward the pole. And it's also going to be moving toward the pole when r is less than 0, which means r is negative, and dr d theta is positive, which means that r is increasing. So if r is negative and r